Hi everyone, my name is Esther and welcome to my assignment 2 presentation for COS10004 Computer Systems. So today I'm going to talk about some interesting topics including microprocessors versus microcontrollers, how scripts can get converted into CPU instructions, programming language generations, Python versus assembly language comparison, and finally, a small research challenge using GPIO on the Raspberry Pi. So here is the overview of what I will be covering. First, we are going to settle the debate, the microprocessor versus the microcontroller. Basically, what is the difference and why should you care about it? Then we'll look about the journey of the code, like how do English words on my screen turn into electricity in the CPU. And we will quickly cover the generations of the languages, basically the history of the coding. Then comes to the fun part, the fight of the generations. So I will show you about a Python calculator versus an assembly language calculator. Then finally, I will talk about a research challenge where I got a Raspberry Pi to blink some LED. So let's start with the microprocessors. A microprocessor, or we call it MPU, is basically a CPU placed on a single chip. It contains millions, sometimes even billions of transistors packed together to process data. MPUs are used in devices that need powerful computation, things like PCs, laptops, servers, and even smartphones. Now let's quickly break down the main components of a microprocessor. So first, the arithmetic logic unit, which is ALU, is like the math engine, and it handles calculations and comparisons. Next is the control unit, or we call it CU. It acts like the traffic controller inside the CPU, and it tells other parts what to do. Next is the registers. Registers are tiny, very fast storage spaces, and they are used to hold temporary values during the processing. Next is the cache memory. It is the high-speed memory built right next to the CPU to speed things up. And next is the processor cores. Processor cores are the individual processing units inside a chip. Modern processors have multiple cores, so they can multitask better. And finally, buses. Buses, which are like the roads that move data around inside the system. So yeah, the microprocessor is basically the heart and the brain of the modern computers. So now I will talk about some real-world examples of the microprocessor. So first one is the Intel Core i7. So these are found in many laptops and desktops because they are very strong performance, great for multitasking, gaming, and productivity. Next is the AMD Ryzen 7. So it is also similar performance as the Intel's Core i7, but often with more threads. Ryzen chips are really popular for gaming and content creation. And the last one is the Apple M2. So this is the Apple's ARM-based chip that appears in MacBooks and iPads. It's powerful and also super power efficient, which is why the battery life of MacBooks is so good. And each of these represents different architecture, but they all share the same purpose, is to provide the high performance computing. Alright, now let's move to the microcontrollers, or usually we call it MCU. A microcontroller is actually very different from a microprocessor. Think of a microcontroller as a mini computer on a single chip. It has a CPU, RAM, flash memory, and built-in peripherals all in one. So microcontrollers are used in embedded systems where the device only needs to do one main task. So example, like washing machines, microwaves, IoT sensors, LED controllers, like smart home devices, and so on. So the components are similar in concept, but smaller and simpler compared to the microprocessor. So first, it has a CPU, which runs the program, just like in the microprocessor. And next is the flash memories, which stores the code permanently. And the RAM stores the temporary data. And the last one is the peripherals, including things like input and output pins, ADC converters, timers, counters, communication modules like SPI, UART, and I2C. So basically, while a microprocessor is the brain for the big computers, and the microcontroller is the brain for the tiny dedicated devices. So here is the examples of the microcontrollers. So first is the ATmega 32P, which you probably know from the Arduino Uno boards. So it is super popular for beginners, DIY electronics, basic robotics, and simple control applications. Next is the PIC16F877A from Microchip. So this one is often used in industrial electronics, automatic sensors, and consumer devices. And the last one is the STM32F103. So it is the part of the STM32 family. So this is a much more popular 32-bit microcontroller used in the IoT devices and like medical equipment, robotics, and drones. So the microcontrollers come in many varieties, from a simple 8-bit chips to a full 32-bit ARM Cortex microcontrollers. Now I will continue the main differences between a microprocessor and a microcontroller. So for the applications, the microprocessor is used for heavy performance-based tasks like running a Windows or a Mac OS. And for the microcontroller, it is for small and low power embedded tasks. Next is the instruction set. So the MPU usually have complex ISA and the MCU usually have the simpler RSSC. Next is the performance. So the microprocessor runs at a high clock speed, usually above 1 GHz. And for the microcontroller, it usually runs below 200 MHz, but are extremely power efficient. And for the cost, the microcontrollers are more expensive and used in the performance devices, but for the microcontroller are cheap and used in mass-produced embedded system. So overall, the microprocessor focus on power, but the microcontrollers focus on simplicity and efficiency. Next, let's talk about how our code actually becomes CPU instructions. So when we write a program in a high-level language like Python or C, the CPU can't understand it directly. The CPU only understands the machine code, which is the binary. So the conversion process normally involves the compiler, which translates the whole high-level code into the machine code. And it goes through steps like lexical analysis, syntax parsing, semantic checking, optimization, and code generation. Next goes to the linker. So after the compiler breaks your code into object files, the linker will connect everything together into one final executable program. And next is the assembler. So if you are using assembly language, the assembler will convert the mnemonics like move or add into machine code. So next, the interpreter, it will run your code line by line without fully compiling it first. So then the last one is the hybrid or the JIT, which is the just-in-time. So this approach the compiles some hot code at runtime, like how Java and newer Python implementation works. So that's how a simple script eventually becomes a CPU instructions. As we know, the programming languages have evolved over decades. They are grouped into generations to show how they are advanced. So they are categorized into first to fourth generation languages. For the first generation is the machine code, and the second generation is the assembly language. The third generation is the high-level languages, and the fourth generation is the very high-level languages. So each generation moves further away from machine details and becomes easier for human to use. Now we look at the first and the second generation languages. The first generation language is the machine code, literally the binary numbers like 0 and 1. So human can't read it easily, but the CPUs can understand it directly. So the main advantages is it has the fastest speed and direct hardware management. But how about the disadvantages? So it is pretty much impossible to write by hand, error prone, and completely tied to a specific CPU architecture. Next, we move to the second generation language, which is the assembly language. So instead of using zeros and ones, you use the mnemonics like move, add, or sub. So you still need an assembler to convert it into the machine code because it is more readable than binary, but still very low level and not portable across different CPUs. So assembly is mostly used in embedded system, performance critical code, firmware, and device drivers. The third generation languages include like C, Python, Java, C++, or more. And these languages let us think in terms of logic, not hardware. They use compilers and interpreters and are much easier to write, debug, and maintain. The trade-off is slightly lower performance, but for most applications, it worth it. So now it's the fourth generation languages, which is the very high level language. So examples include the SQL for databases and MATLAB for mathematical computations. The advantage is fewer lines of code and fast development time. But the disadvantages is less flexibility and less control over the hardware. So part 3 of this assignment, I have built a small calculator program that asks the user to enter two numbers and then outputs the result of the addition and the subtraction. So I have implemented the exact same functionality in Python and in the assembly language, so we can compare them. Alright, so let's look at the Python version of the calculator first. So I started the program with a while through loop on line 1. This is really important because I don't want the calculator to just do one math problem and then close it immediately. I want it to stay open and keep asking for new commands until I tell it to stop. So next, starting from line 2, I have print the menu, which is the Python calculator. Next is the one for the addition, second for the subtraction, and third for the exit. Then I have input an option which asks user to choose operation 1 or 2 or 3. And if the user input to choose 1, so it will perform the addition. So I have input the variable number 1 and input the variable number 2. So it will add the result together, which add the result number 1 plus number 2. So in conclusion, it will print the result of the addition of number 1 and number 2 is the result of the addition. So next, if the option user choose to operate number 2, which is the subtraction, so it will go to the option 2, then continues again. So it will ask for the number 1 and enter the number 2. So the subtraction will do the result, which is the number 1 minus the number 2. So it also will print the result of subtraction of number 1 and number 2 is, and the result of the subtraction. So if the user choose 3, it will exit the program and print the message about like exiting the calculator goodbye. So if the user type the command other than 1 and 2 and 3, it will show invalid option. So this is the result output of the Python code. So when we run the program, the menu calculator will be shown, and it will ask for the operation, choose 1, 2, or 3. So like in this case, if the user choose 1, it will ask for the enter the first number and enter for the second number. So it will calculate the result of the addition of number 1 and number 2 and for the addition of the result. So the program will continue run because we have implemented the while through loop. So if I didn't ask the program to stop, it will don't stop. So now it will continue the program. So when the user choose 2, which is the subtraction, so it will again ask for the first number and ask for the second number. So it will calculate the result of the subtraction, which is the number 1 minus the number 2. Then it will give the result of the subtraction. And again, it will run the program until I choose the operation 3, then it will exit the program and print the exiting message, which is the exiting the calculator goodbye. So now we continue the assembly language of the calculator. So we start with the .data section. In Python, I just type the variables whenever I needed them. But in assembly language, I have to declare everything upfront. So now we look at the menu and the messages. So look at all these lines are just text. So I have to define the label menu using ASCII to tell the assembler that it is a null-terminated string, and then type out the text. So I have to do this for every single question I ask, like enter the first number, enter the second number, and the result is. And again, the enter first number, enter second number, the result of the subtraction is. And also the exit message and the invalid message. Next, we check about the scan pattern. So scan pattern, we need to define a specific string to tell the computer. So this is now we are going to read about a decimal number. So we need to define a string which is the integer so that the scan pattern can define this is a integer we want to use. And next is for the dot word. So because we are reserving memory space for our variables like number 1, number 2, and option. So I'm initializing them to 0 with the dot word. So these are the physical spots in memory where my numbers will live. And next we look at the dot text section. So I have created a label called main loop, and this is like the while through loop in the Python in the line 1, code line 1. So if I didn't end the program, it will not, it doesn't stop, it will continue. So to print the menu, I can't just say print. So in assembly languages, I have to load the address of my menu string into register X0 using LDR. Then I branch with the link using BL to the printf function. So yeah, these two steps is just to print the menu message. Then go to the read option block. So scanning input is even trickier. So I have to load the scan pattern into the register the register X0. Then I load the address of my option variable into register X1. So basically, I'm telling the CPU like use this pattern to read a number and stick it into a specific memory box. Then continue to the compare the CMP and the VQ block. So now for the logic. So I have logged the user's choice into a register. So let's call it W1. So and I use the CMP, which is the compare, to compare it to the number 1. So if it is equal, which is the VQ block, so I will jump it to the addition level. Then if it is 2, I will jump to the subtraction. And it is basically a manual if statement made of jumps. So now continue to the addition level. So first I have to prompt the user again. So I will print the message, print to ask user to enter the number 1 and the number 2. Then now is the important part. So look at the actual math part here. So to add two numbers, I can't just add two variables. I have to load the value of number 1 in the register W1 and load the number 2 in the register W2. Then I will use the instruction add W3, W1, and W2, which means that I add W1 and W2 into W3. Then goes to the subtraction part. It's the same as the addition part, just to change the addition to subtract, which addition is use 8. The plus, the add the number together, and subtraction is minus the number. And after the subtraction operation, it also goes to the sub W3, W1, and W2, which means that W1 minus W2 equals W3. So finally, we will exit when we scroll down to see the exit program. So we have the exit program label. So in the Python, we just use break. But in here, we have to talk to the operating system directly. So I move the 0 into W0, which means return success. And then I move the 93 into X at. Why 93? Because That is the specific system call number for exit in Linux. And then use the SVC #0 is the supervisor call. So yeah, so basically it can exit the program. So this is the result of the assembly language. Basically, it's the same output as the Python result output. So when we run the program, the menu will be shown. So it will ask user to choose operation 1, 2, or 3. So if user choose 1, it will ask user to enter the first number and enter the second number. Then the result of addition will be come out. Then the program is still running because we have implemented the while implementation. So when the user choose operation 2, so it will ask the user to enter the first number and enter the second number. So the result of the subtraction will be number 1 minus number 2 become the result of the subtraction. Then if the user choose the operation 3, which is exit the program, then the program will be end. So here is a quick comparison between the Python and the assembly language. So first is for the lines of code. So obviously the Python is short and the assembly language is long. And for the efficiency, so Python is easier to maintain and the assembly language is harder but give more control. And for the accuracy, both of the languages give the correct answer, but assembly needs to manual overflow the handling. And for the memory usage, the Python uses more memory because of the interpreter, and the assembly is extremely lightweight. And for the developer productivity, of course, the Python is much faster to write, and the assembly language need more time to write it. So this is a clear comparison of the Python and the assembly language. For the research challenge, I've used a Raspberry Pi and built a small program that detects a button press and makes the LED blink 5 times. For the hardware setup, I have used GPIO pins where one pin reads input from a push button and another pin outputs a signal of the LED. So the hardware setup, I have used one LED and one button, and of course the microcontroller, which is the Raspberry Pi 4. So this is the hardware setup. So the button is connected to the GPIO pin 23, and for the LED is connected to the GPIO pin 18. And the negative side of the circuit is connected to the ground, and which is connected to the GND pin. And for the positive LAN, it is connected to the 3.3 volt, which is the 3.3 volt pin. So overall of the setup is when the button is pressed, the program will begin and the LED will be blinking 5 times. Then it will stop. And when we press again, it will blink 5 times until we end the program. So this is the pattern of the research challenge. So in this case, we have set the LED to 18 and the button to 23. So first when we start the program, we have print out the start message, press the button to start the LED blinking, and press Ctrl C to exit. Then we start run the program. So we have implement a while statement there. So while true. So if the program is not exit, it will continue run. And if the GPIO input of the button pin is low, which means when the button is pressed, so the button message will be occur, which is the button press blinking LED 5 times will occur. So when the button is pressed, the message is out. Then the LED will start to blink 5 times. After that, the code for I in range 5, which means that the LED will blink 5 times. After the 5 times, it will print a message that blink sequence complete. After that, the program is continue run. Then if you press the button again, the LED will blink 5 times again, then print the message. Then it runs again. If you press the button again, the LED will blink 5 times until if we press Ctrl C, which is the accept keyboard interrupt, which means that you enter any of the key on the keyboard, then it will print the exiting program and it will exit the program. Then finally, the program will not run, then the button cannot be pressed. Yeah, that's all. So basically this is the research challenge of the Python code. Yeah. So this is the result of the Python language. So when we run the program, so it will print the message. Press the button to start the LED blinking. So after that, we will press the hardware setup of the button. Then when the button is pressed, then the button press blinking 5 times, the message will be pop up until we press the Ctrl C, then it will exit the program. So this is the hardware result output. So when we start the program, we can press the button. So it will blink 5 times. Then it will stop. So the message of the blinking message will occur, and when we press again, it will blink 5 times. And also the message will be printed. And if we press again the button 5 times, it will blink 5 times and the message will be printed. Until if we press the Ctrl C, then it will exit the program. After we exit the program, the button cannot be pressed up because it already exit the program. And that's all from me. Thank you.